So in today's lecture, we are going to talk about the self-induction and the self-inductance. We'll learn what is exactly the self-induction is, and then further we'll derive what is the self-inductance for the solenoid. So before moving on this term of the self-induction, we need to understand what is the induction. So to understand this induction term, let's suppose we have a loop like this. Okay, it is just a loop you can assume, and then there is some ammeter connected to it, and let us take this as the magnet. If I move this magnet nearby this loop, then I will be able to observe that this ammeter will show the deflection. Now this is called as the induction, or exactly the electromagnetic induction. All right, so this is a term where we say that if we take, this is the loop and some magnet is there, and when we move the magnet, so then the flux through this will change with the time. It won't be constant. So then according to the Faraday's law, the EMF which is induced in this is d phi by dt, and this process is called as the electromagnetic induction. Now same like that, let us think a loop that is connected to some source of the power. Let's suppose it is connected to some battery. Okay, this loop is there and it is connected to some battery like this. All right, and this battery is giving the current into this. All right, so then what will happen? Let's suppose this current is variable. This current is changing with the time. Let's suppose we have a variable resistance, or we have the variable battery, or we might be having a AC current, alternating current. So when this current is passing through this, it is also generating the magnetic field. And you know that the magnetic field at the center of this is mu naught I divided by 2R. This is the magnetic field at the center of a loop. Okay. Now, if I change the current passing through this loop, then the magnetic field will change, and the flux through this, we can say that this is B vector dot A vector, which is basically mu naught I divided by 2R multiplied by area of the loop A. This is the flux. Tell me, this flux, will it change with the time if I change the current which is passing through this loop? Yes. So it is changing. So because of that, now there is a EMF which is d phi by dt, and which can be written down as d by dt, and phi flux is mu naught IA divided by 2R. All right. So this current is changing, and because of the change in the current, there is some electromotive force EMF generated in that. Now this EMF is generated because of the current which is passing through this loop only, and this EMF is going to oppose the change in the current, and this process is called as the self-induction. Why we are calling it as the self-induction? Because there is no other thing, there is no other magnet, or there is no other source which is changing the magnetic field passing through this loop. It is the loop itself which has some current, so because of that there is a flux, and that flux is changing with the time. So that is why we term it as the self-induction. And now there is some property related to the self-induction. That property is called as the self-inductance. All right, so let us take a solenoid. We are going to derive what is the self-inductance for a solenoid. So you know what is the solenoid? We take a wire and then we wind it, we closely wind it like this, and we form kind of a cylinder. This arrangement is called a solenoid, which has a very small radius. Let's suppose length of the inductor, and the solenoid is also called as the inductor when it does the self-induction. So we are calling it as inductor, and the length of this total length is L, and the total number of the loops per unit length are small n, and I is the current passing through it. So to get to this property of self-inductance, first we need to write down what is the flux. So to write down the flux, we need the magnetic field. Now the magnetic field passing through the solenoid is, for a ideal solenoid, is B equals to mu naught Ni. Okay. Although you might be knowing the other formula, mu naught Ni divided by 2 cos theta 1 minus cos theta 2. This is for a small solenoid. Now I am taking a big solenoid with a small radius, so I can apply the approximation of theta 1 taking 0 and the theta 2 taking 180 degree. So magnetic field in the solenoid is mu naught Ni. All right. Now what is the flux? Flux is mu naught Ni. This is the magnetic field multiplied by area. Area of this, let us take, is the cross section of inductor. Okay. Now the problem with this flux is that this is the flux because of or passing through just one of the coil. How many coils are there in this solenoid? So look, in per unit length there are small n coils and that's the total length L. So the total number of the coils would be small n multiplied by L. So that is why the total flux is going to be total number of the coils multiplied by flux passing through one of the coil. So phi naught, let us call it as, that is n multiplied by L multiplied by mu naught n I A. Let us simplify this term. So flux becomes mu naught n square I A L. Okay, this is the flux. Let me just rearrange it again. Mu naught n square A L multiplied by I. Okay, I is the current passing through it. Now let us find out, according to the Faraday's law, what will be the EMF generated in it. So EMF is going to be d phi by dt. Okay, I am not taking negative positive, it is just the value. So d by dt of this will be, we know that all these properties are constant, just the current is changing. So mu naught n square AL multiplied by di by dt. And now this remaining term is called as the inductance or the self-inductance. So self-inductance is going to be mu naught n square AL. This is the self-inductance of a complete solenoid, or you can say inductor, of having small n number of loops per unit length, and A is the cross section area, L is the total length of this inductor. All right, so we can say that if you want to calculate anywhere else, one way to calculate this inductance is, you can say that the EMF generated in that is L di by dt or minus L di by dt. So you can calculate the EMF generated in that because of the change in the current of the loop itself, and then you can just compare and then you can find out the L value. Or otherwise you can say flux passing through a solenoid or any of the loop is Li, where L term is the self-inductance of that. Okay, now this property is entirely dependent on the inductor's geometry, and it is basically the volume and the number of turns per unit length, and it is based on the material of the solenoid or the inductor as well. If you put any other material, so then we'll write down that the inductance is mu naught mu r n square AL. This is the inductance if we take any other material. All right. What is the unit of this inductance? So this inductance SI unit is Henry. So I hope you must have understood what is exactly the self-induction, phenomena of self-induction is, and what is the self-inductance. And then you can also watch other videos available on the channel. I will also make another video on the mutual inductance. All right, thank you.